Post this to YouTube later on about 3 or 4 o'clock or something like that. We're going to move on to something called Le Chatelier's principle. And Le Chatelier's principle has basically no math in it. This entire booklet has basically no math in it. Okay? As long as you can count to 5, you'll be good to go with this kind of stuff. Now, unfortunately, because there's no math, or very little math, that means it's very concept heavy. So for the people who like math, they like the square root stuff that we were just working on, but they don't like the concept heavy stuff, this is going to be a little bit maybe annoying. But that's fine, that's okay. We'll get through it together. We're a team. We got this. You got this. Le Chatelier's principle. It basically says a disruption to a chemical system at equilibrium by changing a property of the system. The equilibrium will shift to oppose the change until a new equilibrium is established. So that's a lot of gobbledygook. What it means, all it means is, do you remember when we were just talking about the equilibrium graphs? And it was like, well, if you've got substance A and you've got substance B, and they react together, this is kind of how the equilibrium graph looks like. Do you remember kind of talking about that? Okay. So once we've maintained equilibrium, what we can do is we can disturb this equilibrium. We can disturb it in a bunch of different ways. There's kind of 3 main ways we can disturb this equilibrium. If I added a bunch of B to this container, if the concentration of B all of a sudden shot up, would this system be in equilibrium still? No, because it's not maintaining that same ratio of A to B, right? Other things we could do, we could change the volume or the pressure in the system. We could change the temperature in the system, right? What do I do to an equilibrium? What do I change by heating up or cooling down a system? What do I change by changing the temperature? Do you remember? Kc, the value of Kc. So in this particular reaction, right? A is reacting with B. It's got nothing to do with this here. Okay, so I'm just going to erase that. In this particular reaction, A reacts with B to make AB, and the Kc is 0.15 at 20 degrees Celsius, or something like that. If I heat up this system, or if I cool down the system, this number changes. And I will show you in this notes package how to predict whether or not the Kc goes up or goes down. What I want you to do is I want you to write the equilibrium reaction, this equilibrium reaction, as 2 separate reactions. Go ahead and do that. This is secretly hidden in here are 2 reactions. Would you agree with that? There's the forwards reaction, and what else? The reverse reaction. That's one of the reactions that's going on here. The other reaction, and we'll just write it out. Would you agree those are the 2 reactions that are being represented by the equilibrium arrows? Forwards and the reverse reaction. Okay. Now, once equilibrium is established, this system is at equilibrium. Here's a container, and we've got A's and B's, and we've got AB's, and they're all mixed together. Now, I can't draw a dynamic equilibrium. I need you to understand that, right? Can you agree that it's very hard for me to draw that this A, this B, they're combining together to form AB, and this AB is splitting up to make A and B, right? And they're happening at the same rate. For every AB that we make, there's one AB that breaks up into A's and B's. Does that make sense? That's the definition of equal grids, right? Okay. What would happen to these 2 reactions if you removed all of the AB from this container. So if I took the AB, don't write this down, what I'm about to do, but if I took this AB and I removed all of the AB, I want you to think hard. What effect would that have on the top reaction? Would this top reaction increase, decrease, or would the rate of the reaction, how fast these things react, would it stay the same? What do you think? What am I affecting by getting rid of AB? Am I affecting the reactants or am I affecting the products here? Have I physically done anything to the A's and the B's? I haven't physically done anything. So this amount is staying steady, right? Are they still able to react with each other and turn into ABs? Yes. So there's no effect. There's zero effect on the forwards reaction. Would you agree? There's no effect, right? But what about the reverse reaction? What about ABs turning into A's and B's? Have I affected this reaction? Are there any ABs to turn into A's and B's? No. So what I want you to think about, by taking away all of the AB, we only have forwards reaction going on. There's no reverse reaction possible. Does that make sense? Have I thrown this system out of equilibrium temporarily by doing that? Yeah, I have, yeah. So what would happen to the mixture of these two reactions if you removed all the AB? Well, the forward reaction is unaffected. But the reverse reaction would slow down. By taking away all the ABs, I've affected the reverse reaction, but I haven't affected the forwards reaction at all, right? The A's and B's, they're still unaffected, whatever, it doesn't really matter. Okay, let's take a look at the second case. What would happen to these two reactions, right, the forwards and the reverse reaction, if you quadruple the concentration of AB? Okay, so I get to do this, you don't. It's a little bit unfortunate, but that's life. If I quadruple the concentration of AB in here, okay? Now, have I affected, I'm curious, have I affected the forwards reaction? Did I change the amounts of A and B in here by doing that? Oh, well again, the forwards reaction is totally unaffected, right? What about the reverse reaction? Every second, are there more ABs turning into A's and B's, or are there less ABs turning into A's and B's now? There are way more of these, right? So way more of these are available to react. Would you agree? So the reverse reaction, what? Did we speed it up or did we slow it down? Yeah. So the reverse reaction is, I don't know how to say this. My brain's not working. Sped up. I don't know. Is that even a word? Yeah, increase. The rate of the reverse reaction is increased. Whatever. Okay? So we're increasing the rate of that reverse reaction. That's what we should say. Now, so hopefully you can see by adding something or taking away something, we've changed this system's equilibrium. We're either increasing or decreasing the speed of one of these reactions. And I know that that's not particularly exciting. I get that that doesn't, get you up in the morning or something like that, okay? But It's important for you to keep that in the back of your mind, that this is everything 15.2 is about. Throwing the system out of equilibrium, and how does it get back into equilibrium? There are 3 disturbances which a system can resist, okay? We can do this to a system, and the system will claw its way back into equilibrium, okay? We can change the concentration of reactants or products. I'm lazy. Hopefully you know what that means. We can also make a change in the temperature of the system. It will claw back to equilibrium, but not the same equilibrium it was before. We can also change the pressure inside of a container. Usually that's by changing the volume, right? If I have a bunch of gas particles, in a box, what's going to happen to the pressure inside here if I condense the box, if I decrease the volume? Is the pressure going to go up or down? We'll think about that. Okay, so let's move. So in general, the things that we're worried about for Le Chatelier's principle, we're worried about graphs. We're really worried about graphs because graphs give us a lot of information in a very short amount of time. One graph is worth 10,000 words, that kind of thing, okay? So what's happening here? We've got some dinitrogen tetroxide, and we're adding heat to it, okay? Or it needs heat in order to react, and it will turn into 2 NO2 molecules. So here's what we've got going on. We've got a system, and is the system at the beginning, let's take a look at it, is the system already in equilibrium? Yes, it is. Would you agree? Right from the get-go, it's already in equilibrium. How do you know it's already in equilibrium? Because they're straight lines, yeah. Because these concentrations aren't changing. Then what we do, right at 2 minutes, we do something to this system. What is it that we did to the system? Look at the kind of bottom half of your page. It's not on my slide, but we increased the temperature. And when we increased the temperature, we threw this system out of equilibrium. Now, if you gave it a little bit more time, does the system immediately get back into equilibrium? No. It slowly over time gets back into equilibrium. The concentrations change really rapidly at first, and then they start to slow down, okay? What's happening here is when I increase heat, when I increase the temperature of this system, I'm basically increasing the rate of the forwards reaction. You can think of energy and heat as like an entity inside this chemical reaction. If I add heat, okay, am I increasing the forwards reaction or am I increasing the reverse reaction? I'm increasing the forwards reaction because it's a reactant here. It's not a product, it's a reactant. By adding temperature, I'm adding a reactant, and I'm forcing the forwards reaction to increase its rate, okay? So what happens is, by increasing the forwards rate, I'm decreasing N2O to N2O4, and I'm increasing NO2. So I'm decreasing N2O4, and I'm increasing NO2. It doesn't matter right now. The specifics aren't super important. But as long as you kind of understand, we've got an initial equilibrium, like original equilibrium. We do something to that equilibrium. It shifts, and then we establish a new equilibrium. Every single time, that's what's going to happen. We're going to have an equilibrium. We do something to it. Things change, and then we establish a new equilibrium. When substances are added, the equilibrium will shift to opposed direction to use up the extra substances. So what would happen to the system if HCl gas is added at point A? Would you agree? We've established an equilibrium here, right? We've got some sort of initial conditions, and we establish an equilibrium. Now, I'm adding a chemical. What am I adding to this system? If I add HCl gas, okay, which line is HCl gas? Top, middle, or bottom? Bottom, okay? So what's going to happen is I'm going to increase immediately the HCl concentration. It spikes up. Have I thrown this system out of equilibrium? Yes, I have. I totally have, right? Absolutely I have. I can be able to do that today. By increasing the HCl concentration, am I changing the rate of the forwards reaction, or am I changing the rate of the reverse reaction?
This is a reminder to all students that basketball
We'll think about that.
at 11:55.
We'll talk about that tomorrow.
Teachers, Duncan.